On July 4, 2012, the ATLAS and CMS experiments announced the discovery of a new particle near 125 gigaelectronvolts. Measurements of its spin, production, and decays later established it as the Higgs boson predicted by the Standard Model. That discovery completed the Standard Model particle spectrum, but not our understanding of the Higgs sector. We have measured many interactions of the Higgs with fermions and gauge bosons. One fundamental interaction remains unobserved: the interaction of the Higgs field with itself. To test that interaction directly, one Higgs is not enough. We need two.
The question begins with the Higgs potential. Its minimum occurs at a non-zero field value, so the Higgs field acquires a vacuum expectation value of about 246 gigaelectronvolts, spontaneously breaking electroweak symmetry. Writing the physical field h as a fluctuation around that vacuum gives terms proportional to h squared, h to the 3, and h to the 4. The quadratic term determines the Higgs mass, the local curvature of the potential. The cubic term produces the trilinear Higgs self-interaction, and the quartic term produces the 4 Higgs self-interaction. In the Standard Model, the measured Higgs mass and vacuum value predict these couplings, but prediction is not measurement.
Measuring the curvature at the minimum does not independently verify the third and fourth derivatives of the potential. The fields or higher dimensional interactions could distort the potential while leaving many single Higgs observables nearly unchanged, and could even modify the electroweak phase transition in the early universe. The leading direct probe of the third derivative is Higgs pair production. At the LHC, most Higgs pairs are produced through gluon-fusion. Because the Higgs has no tree-level coupling to gluons, virtual top quarks mediate the process. At leading order, two amplitudes dominate. In the triangle amplitude, two gluons produce an off-shell Higgs through a top quark loop. It then splits into two through the trilinear self-interaction, whose strengths we describe with kappa lambda. In the box amplitude, the top quark loop produces both Higgs bosons directly without the trilinear vertex. These histories connect the same initial and final states, so their amplitudes must be added before squaring. Around the Standard Model point, they interfere destructively, and this gives a remarkable result. Switching off the trilinear coupling removes the triangle amplitude, but also removes part of the cancellation. So the Higgs pair rate increases. Changing kappa lambda also reshapes the pair invariant mass and other kinematic distributions. A Higgs pair analysis is therefore not simply counting rare events. It is reconstructing a quantum interference pattern across phase space. Vector-boson fusion provides a complementary probe. Two incoming quarks radiate W or Z bosons and continue as energetic forward jets. The vector bosons interact to produce the Higgs pair. Several amplitudes contribute, including one involving the trilinear coupling and another containing the direct VV-HH interaction, parameterized by kappa 2V. For longitudinal vector bosons, Standard Model cancellations control the high energy behavior. If kappa 2V differs from 1, the high mass tail can grow dramatically. Experimentally, neither Higgs reaches the detector. Reconstruct the pair from its decay products. Four bottom quarks provide the largest branching fraction, but face enormous multi-jet backgrounds. Bottom quarks plus photons sacrifice rate for exceptional mass resolution. Taus and vector bosons provide complementary signatures. No signal channel is ideal. The strongest constraints come from combining decay modes, production mechanisms, and event topologies. As of July 2026, Standard Model Higgs pair production has not yet been observed. The first combined ATLAS and CMS round 2 result limits the total production rate to 2 times the Standard Model prediction at 95% confidence. The Standard Model is consistent with the data, but the Higgs potential is still only loosely mapped. Looking ahead, the High-Luminosity LHC is scheduled to begin operation in 2030, ultimately delivering about 10 times the LHC's original design luminosity. That enormous increase in collision statistics will give us far greater access to rare processes like Higgs pair production. One Higgs established the particle, two Higgs bosons begin to map the potential, and three begin to reach its next derivative. The Higgs boson was discovered in 2012. The landscape behind it is the discovery now ahead of us.